Far beyond the coastline, an impossible city appears to float above the Pacific. But this ocean can generate 15-meter waves and Earth's most powerful storms.
Today, we reveal how China could engineer this revolutionary floating transportation megaproject.
The central question was simple. Could an entire transportation city survive out here?
Subscribe and follow every engineering step, from first survey to full operation.
Powerful currents would constantly twist, lift, and pull different structural sections. Saltwater corrosion could destroy ordinary steel connections before construction was even completed.
Deep water eliminated conventional foundations and complicated every offshore supply operation.
Decades of records confirmed repeatedly exposure to typhoons, surges, and extreme winds. S-21 remains an engineering concept, testing what future construction might achieve.
China's busiest coastal hubs already process enormous cargo and passenger volumes. Limited berths force ships to wait, increasing fuel use, delays, and costs. Expanding airports and logistics zones requires scarce and extremely valuable coastal land.
The concept connects sea, air, cargo, passengers, and emergency transportation offshore. Separating passenger and freight circulation would reduce congestion across the entire facility.
A central aviation platform could move emergency supplies beyond crowded airport runways.
The city would provide protected living space for workers stationed far offshore.
Independent generation would reduce dependence on vulnerable power cables returning to shore.
Onboard desalination would supply drinking water during prolonged mainland service interruptions.
Every system had to remain safe, expandable, self-sufficient, and continuously operational.
Before designing anything, engineers needed an accurate ocean and seabed model. Autonomous vessels mapped currents and depth without constantly exposing crews to danger.
Multi-beam sonar revealed ridges, sediment channels, depressions, and possible anchor locations.
Sub-bottom profiling tested whether buried soils could resist long-term anchor loading.
Core samples identified soft mud, dense sand, gravel, and deeper bedrock. Laboratory tests measured density, shear strength, compressibility, and repeated load resistance.
Current sensors recorded water movement near the surface and along the seabed.
A full seasonal record captured conditions that short surveys could easily miss.
Drones measured how floating test structures responded to real waves and winds. The first hidden risk was weak seabed beneath several planned anchors. A deeper current created an unseen sideways force beneath the northern platform. Lead engineer Liam Walker now faced the project's defining structural problem. A rigid ring concentrated enormous stress where wave crests lifted individual sections.
Independent modules reduced stress but could not maintain reliable transportation connections.
Conventional piles were impractical because stable rock lay far beneath soft sediment.
Land reclamation required immense material and still risked dangerous, uneven settlement. The central tower added wind loads capable of rotating the entire structure. Daily operations would shift thousands of tons between different platform sectors. Passive ballast could not respond quickly enough to sudden asymmetric loading. Every exposed connection needed protection from salt, humidity, vibration, and ultraviolet radiation.
Emergency access was difficult because residents could be kilometers from central refuge.
The city needed flexibility, independence, isolation, and continuous central coordination.
The final solution had to float, flex, stabilize, isolate damage, and connect.
4 layouts were compared for wave response, circulation, expansion, and construction complexity.
The circular form distributed wave energy more evenly around its perimeter.
Engineers divided the ring into replaceable arc modules instead of one hull.
Each compartmentalized UHPC hull remained buoyant after localized structural damage. Watertight bulkheads prevented local flooding from spreading through the entire module. Active ballast pumps shifted water automatically against waves and changing operational loads.
Dynamic stabilizers generated corrective force before rolling motion became dangerous.
Articulated connectors allowed movement while preserving pedestrian, utility, and service links.
Laminated structural glass protected biomes without adding excessive hull weight. The central core supported navigation, administration, emergencies, and the elevated helipad.
Distributed moorings restrained drift while permitting safe vertical movement with waves.
The torus balanced structural flexibility, modular construction, and operational redundancy.
Construction began onshore, where massive components could be produced under control.
Jack Bennett divided the fabrication yard into casting, assembly, and inspection sectors.
Dedicated power systems supplied casting plants, robotic welders, cranes, and controls.
The specialized plant produced dense concrete with extremely low saltwater permeability.
Controlled storage prevented moisture and salt from changing the concrete mixture.
Transfer rails moved completed sections safely between casting and outfitting stations. The dry dock would launch modules without enormous land-based transporters. High-capacity gantries would lift steel frames and glass ribs with precision. A millimeter accuracy network controlled every major fabrication and assembly operation.
A dedicated fleet prepared to move components 50 kilometers offshore.
The reinforcement cage rolls into the casting station as Jack gives the production signal. Reinforcement was bent to match each arc module's precise structural geometry.
Robots positioned thousands of bars while preserving pipe and inspection clearances.
Critical systems were installed before becoming inaccessible inside the completed hull.
Continuous placement prevented cold joints under repeated offshore wave loading. Careful consolidation removed voids where salt water could reach the reinforcement. Controlled curing limited thermal cracking across the enormous concrete section.
Subscribe as Cole guides the first massive hull through precision manufacturing.
Curved alloy ribs formed the lightweight skeleton supporting each glass enclosure.
Controlled welding minimized distortion that could misalign the glass panels.
Emma searched for hidden cracks, voids, and incomplete weld fusion.
Every glass panel faced pressure, debris impact, and marine corrosion testing. Mechanical systems entered before upper decks permanently enclosed the service compartments.
Interior work transformed the shell into a functioning residential biome module. After 18 months, the first complete arc module entered the water.
Offshore assembly began by positioning anchors beyond the weak sediment corridor.
Suction anchors transferred mooring forces into stronger soil beneath surface sediment.
ROVs verified alignment and installed movement, tension, and pressure sensors.
Temporary moorings established a controlled reference point for offshore assembly.
The central plaza arrived in segments sized for heavy offshore lifting.
Guide systems restrained rotation while cranes positioned segments within millimeter tolerances. Mechanical keys connected sections before permanent UHPC joints were injected. The reinforced tower core rose level by level above the platform.
Steel outriggers distributed tower wind loads across the broader central hall.
Factory-built floors accelerated construction while reducing offshore worker exposure. A lightweight composite helipad completed the tower's highest structural element. Tugboats carried the first finished living module slowly toward the offshore site.
Independent thrusters countered currents as the module approached the assembly zone.
Positioning software reduced the remaining separation to only a few centimeters.
Hydraulic capture arms restrained movement before structural locks could engage.
Primary locking pins transferred horizontal forces into the central plaza.
Articulated bridges preserved circulation while allowing controlled wave-induced movement.
Each new module expanded the ring and changed the platform's overall balance. Engineers added modules symmetrically to prevent excessive construction stage tilt.
Flexible joints carried power, water, data, and drainage across moving interfaces.
Only one connection remained before the torus became structurally continuous.
The hardest connection will close under rapidly changing offshore conditions.
Hours before closure, an offshore square developed faster than forecast. Increasing waves repeatedly pushed the module away from target alignment. Rapid deck movement introduced noise into millimeter positioning measurements. One capture arm engaged early, creating force across the unfinished connection.
Temporary connector forces approximately maximum safe values call within seconds. Ryan cleared the deck and suspended every manual coupling operation.
Jack ordered withdrawal before connector housings suffer permanent structural damage.
The closure stopped, leaving the ring incomplete as the storm intensified.
Remote inspection found surface damage and a 4mm coupling misalignment.
Construction could not resume until engineers understood the positioning failure.
Liam compared every sensor stream recorded during the failed closure.
The main error came from delayed wave prediction and corrective thrust.
A slow ballast valve allows several additional millimeters of roll. Technicians installed a faster actuator and recalibrated the ballast control loop. A predictive algorithm calculated movement before each wave reaches the connection. The new system coordinates every tugboat as one positioning machine. Technicians restore coupling geometry and verify every surface against tolerance. Engineers validated the revised process on a full-motion connector test.
When conditions improved, predictive positioning guided the module back into alignment.
Every connector aligned, closing the torus within 2 millimeters. With structure complete, engineers transformed S21 into an operational city.
Integrated photovoltaics supplied daytime power while batteries balanced changing demand.
Marine wind generation supports cloudy weather and nighttime platform operations. Reverse osmosis converts seawater into drinking, irrigation, and service water.
Independent ventilation maintains humidity without spreading smoke during emergencies. Fire protection divides the city into isolated sectors and protected routes. The tower unified maritime traffic, aviation, weather, and rescue coordination. Continuous monitoring detected stress, leakage, corrosion, and connector movement. Dedicated service routes moved supplies without obstructing pedestrians or emergencies. Every module operates independently while remaining synchronized through one control network. Final testing began with an extreme asymmetric load on one sector. Active ballast corrects the tilt before exceeding operational limits. Engineers recreated irregular waves to measure connector movement and damping.
Flexible joints absorb movement without interrupting access or utility service.
Glass enclosures resisted wind-driven water, pressure changes, and simulated debris.
Controlled confirmed flooding neighboring compartments, preserving buoyancy and stability. Battery systems restore control, lighting, pumps, and communications within seconds.
The evacuation drill tested routes, refuge capacity, communication, and medical response.
Pilots tested helipad guidance under crosswind and navigation system failure.
After every trial, S21 received final operational approval.
Subscribe as S21 begins connecting ocean and air on its first day.
The first official aircraft demonstrates rapid offshore emergency and medical access.
Dedicated terminals allow passengers, supplies, and maintenance vessels to operate safely.
Cargo drones urgently delivered goods without consuming airport or harbor capacity.
A self-sufficient community operated above machinery, continuously stabilizing the city. S21 shows how deep ocean engineering can transform impossibility into global infrastructure.